Aha. Channel 1 wena eksterni, znači to je kao...
I'm pleased to introduce Professor Wright.
Dobro, super, hvata nas. Ne, imaš ovo. Ovo imaš. Ovo imaš. To je mikrofon.
Okay. I'm pleased to introduce Professor Rice to tell us about heating and weakening of earthquake faults and rapid slip.
Probaš samo...
Thank you. I'm too old to remember what's on my slides without having a chance to see them. So this is something I've been working on for a long time, starting already in the 1970s. I've begun to think about how ideas from solid fluid mechanics and fractional mechanics in particular could be applied to problems science. And one of the things I've focused on strongly in recent years is how heating during frictional slip interacts and causes the weakening of faults and contributes to the earthquake process. And I've had many co-workers on this, quite brilliant co-workers, fortunately for me, and they're listed down here below, and let's get on with the story. I need another aid, which goes with age. I have one glasses. Yes. So, an old idea, which I think is second nature to anyone who's worked in mechanics or materials science, is the idea that the friction strength is expressed simply as a friction coefficient times the normal stress. And the new wrinkle that we have to put on that
Ovdje zvučnik.
Okay. Well, the new wrinkle that we put on that in the case of faults that are infiltrated with fluid, that's a typical situation of the Earth's shallow crust. Any fault that you have is infiltrated with groundwater, and the pressure in that water is often a major factor in understanding fault response. So the generalization of our normal formula for the shear stress, tau, and friction is that the limiting shear strength is a friction coefficient, which is typically of the order of 0.7 or that ballpark for rocks, times the difference between normal stress and pore pressure. And sometimes that's called the principal of effective stress, but that's the way we represent strength. And another discovery of recent years, which was really a major puzzle, because if you look at a geologic scale at fault zones, you kind of see a broad zone of disruption But one of the amazing discoveries of recent years is the actual zone that slips during ruptures is extremely thin. I'll show you some pictures in a moment which illustrate that, but thin on the scale of millimeters, not meters. And that's the zone that slips. Now, of course, as an earthquake rupture slides along a fault, it is a mode 2 shear crack. It concentrates stress in its vicinity, so it creates a lot of damage, and so cracking and breakup of rocks near an earthquake rupture fault will extend on meter scale off the fault, but the actual slip zone is extremely thin. So that's what we've learned, and that's illustrated on a picture like this. So here on the left, you see a section. The scale was of the order of well, it's marked there, 0.1 meter on the left. So we're seeing a picture of a fault zone. It's not very good, but then when a thin section was made of the region including the zone that slipped, and when that was magnified, this picture on the right was produced, and you see the scale there. I believe it is 5, yes, it's 5 millimeters. And what you see is the zone that actually slipped in the earthquake was incredibly confined, far less than 5 millimeters, in fact less than a millimeter in thickness, a few hundred microns. So all of the destruction done in these big earthquakes is done by slippage on extremely thin zones, mode 2 shear cracks, if you like, or mode 3 sometimes. Okay, so that's that part of the story. Here's another evidence of that. In Taiwan, several years ago, there was a major thrust-like earthquake. So that's the kind of earthquake where the one part of the earth dips down below another part. And after that Taiwan earthquake, people made drill holes down, took out cores, and intersected the fault. And this shows examples of cores that were taken out. And this is a core which, again, illustrates an extremely thin slipping zone, as you see in the picture at the top. If my memory is right, because I can barely read it from here, but yes, it's 50 to 300 microns in thickness, the zone that actually slipped. Now, they're not always that thin, and other intersections of that same fault gave thicknesses that actually were an order of magnitude or more bigger, getting up into even the centimeter range, but still tiny compared to the other dimensions of the earthquake rupture fault. Now, why did it take geologists so long to discover this? And it's basically that they live on the surface of the earth. They don't live in the earth. And they see what they see on the surface, and this is an example of a rupture that took place in Southern California. And you see a very complex sequence of ruptures, but what was done in this case was over a fault which ran coming out of the board towards you along in this picture. This is a vertical cut, and that was made by digging a trench across the fault and mapping out the structures of damage that could be mapped on the wall of the trench as you dug down. And you see there is a broad zone of damage, but as the lower figure shows, as you go down more than a few meters in depth, that is all coalesced into a very thin zone. So yes, near the surface things were complex, but at depth all the slip seems to be on a very confined zone. So that was a major change in the way we thought about faults, and that naturally raises the question, well, what could be going on which causes this localization? And we have a few candidates that we've identified. One is the process that's called flash heating. I'll say more about that, and then I'll go on and
talk about thermal pressurization of in situ pore fluids. Faults live in the earth. The earth is fluid saturated wherever it's porous, so we have to assume that when faulting takes place, there are ground fluids present. But first we begin with flash heating and frictional weakening. So flash heating is an old idea. It was developed principally by Bowden and Tabor at Cambridge in their studies of friction in metals. And it basically never got developed in a way to describe dynamic friction, but that was taken up in recent times principally by the earthquake community. And this is something from one of my papers on it, where you have a blown up picture of a rock on rock contact zone where you have true contact at isolated places. And these isolated places end up carrying gigantic stresses of the normal stresses of the order of 1/10 of the elastic shear modulus. So they're extremely high stresses carried. And if you know the macroscopic shear stress, and if you have indentation measurements which have told you what the normal stress supported the disparity contacts is, you can work out the shear stresses, and they are also quite high. So what we speculate in trying to make a model of this frictional weakening process is that as these asperities are forced to slide, their shear strength is high. Now we're looking, sorry, I've jumped too far. Their shear strength is high, so let's look at the lower diagram. But they get hot, and ultimately as they get hot, they weaken. The ultimate...
Ease your presentation.
Okay, oh good, good. Now no one can see from that side. Sorry, am I blocking the screen for anybody? Let me move back like this. Okay. Sorry, that side of the room, it's not fair. But yes, after a while I'll move over there, remind me. Okay, so the simple assumption is that the shear strength starts high, but things get hot, of course, because of all the heat generation. And once you reach a certain weakening temperature, the friction strength falls off, and that weakening temperature may primarily be due to, can I carry this? Will this work too? Does that work? Yeah, okay, fine. Now I can read my slides too. Okay, so that weakening temperature could be due to the onset of melting. There are other things that might happen as far as just temperature dependence of the dislocation plasticity in the rock. But that's the simple model that we devised. And so you could ask the question, using heat transfer theory, a simple calculation, you could figure out if you slip at a certain rate, what would that rate have to be for an asperity of diameter d? D is my asperity diameter up here. It will get slid out of existence, but if it is just going to reach the weakening temperature as it slides out of existence, and then the friction is negligible or some very small value, that would suggest a friction law, which is the friction factor is its high, slow friction when the velocity is small, but when the velocity is high, asperities weaken during their lifetimes, and you get this other factor. So you end up with predicting a law that looks like friction coefficient is a constant plus another constant divided by velocity. And that's the form that was predicted, and then experimentalists, Tolis and Goldsby at Brown, tried to fit that, and they had an awful lot of ringing in their experiments, as you can see, but what you see plotted here is velocity of sliding versus the sliding displacement in millimeters. And you can see in these tests at different velocities, these are all at moderately high speeds. But by the way, the average slip rate during an earthquake is on the order of 1 meter a second. You can get that because you can look at the amounts of slip in different earthquakes, and you can use seismic methods to figure out what the time duration of the slip was, and it works out to be on the order of 1 meter a second as an average slip speed in an earthquake. And what these experiments show is before you get up to 1 meter a second in slip speed, you do have weakening. So here's the friction coefficient, and it weakens. The theory are these black curves, and the experiments are quite scattered. There's a lot of ringing in that apparatus, but there was also a very elegant experiment done with a so-called torsional Kolsky bar, where you take a rod and you push it into a contact. So here a rock was used as the plate and this annular contact region, and it was all pre-twisted with a clamp here, and then the clamp was released, so a torsional wave propagated down and reflected back. And these experimentalists were able then to actually measure things at rather high slip rates that got into the range of real earthquakes. And again, they saw a pronounced weakening, as you see here, but the experiment was marred by the fact that the specimen walls cracked. So that was suggestive but not definitive. But then later on, Goldsby and Tullis refined their techniques and were able to produce results like this for different rocks: quartzite, novaculite, albite. And you see in all cases they fit very well the simple theoretical expression calculated as I've just explained to you before, that friction should be a value in a weakened state plus a static friction minus that value times a constant that depends on the material divided by the sliding velocity. And this we calculate from thermal and strength properties of the material. And you see that fits pretty well. Here's quartzite, novaculite, and albite, and the experiments and the modeling are on here, and the model works fairly well. So that was, they published that in Science in 2011. So this idea seems to work for faults. It even works much more than we think it should in some cases. Here's an example of a study where the fault was slipped in the laboratory, slipped, and then there was a decrease in the slip rate, and the model fits very well during the slip phase. It fits for a while during the unslipping phase. It becomes poor when the sliding velocity is dropped down a bit.
Jim?
Yes.
Microscope.
Oh, sorry, microscope.
It's okay.
Okay. I've got things in both hands when that hand goes up. Okay, don't be reluctant to prompt like that. Okay, so here was an example where not only during the increase in velocity did the model work, but for more than an order of magnitude decrease in velocity from the higher sliding velocity during the earthquake, it worked. And then it failed to work as we had great reductions in sliding velocity. Again, about 1 meter a second is a typical slip rate during a seismic event. Okay, now this is a digression, and I'll go through it rather fast, but there's also a group of researchers who recently looked at remote imaging of large landslides and tried to work out the mechanics and asked themselves the question of what friction law would be needed at the base of the landslide in order to match the dynamical development of the slide. And they came up with a law which is down here. This is Lucas Mangenet and Ampuero in Paris. And their law was of this form, which basically at large velocities compared to the weakening velocity corresponds to the simple flash heating law. So it looks like such a law also has some degree of validity for very large landslides as well. So how did we get here? This is just reviewing the data you saw before. Now, another thing about this fault gouge material is that the particles get extremely small. So the ground up material in the fault zone gets down to, here you see in a dimension in millimeters, so it gets down to the micron range, and it's a size distribution of the particles. Now, what could cause faults to weaken? We know that they cannot possibly operate at their frictional threshold, because when we try to slide them in the lab at appropriate normal stresses and shear rates, they weaken. You saw that in the experiments. So what could be going on that makes a statically strong fault dynamically weak? And I've explained one possible mechanism already, as well as some of the experimental justification for it, flash heating. I want to now go on to another one which recognizes that the faults are typically fluid saturated, and that as the fluid gets heated up by the frictional heating, the fluid wants to expand, and that increases the pore pressure. We remember, however, that the friction strength is proportional to the difference between the normal stress that clamps the fault shut and the pore pressure. So raising the pore pressure reduces the friction. Now, those are main processes that we look at. Other things more complex can set in with a large enough rise in temperature, and in fact the fault zone minerals may undergo thermal decomposition. So for example, if you have carbonates as the type of rock in the fault zone, these can liberate CO2 at extremely high pressure as they reach these kinds of temperatures, and clays or serpentines in fault zone will release water. And then, of course, the ultimate weakening process, and we don't think it happens very often, but it is the ultimate limit, is melting of the gross melting of the rock. Okay, so here's an attempt to try to understand weakening by fluid pressurization. So the idea is we're sliding one block of rock relative to another one at velocity v. The shearing zone is assumed to be a thickness h. And we ask, does the strain stay homogeneous in that zone, or does it localize, and how localized does it get? And for the calculation I'll show you, we have taken V to be 1 meter a second, which, as I said, is typical of earthquakes, and we've looked at a range of values for H. But what we have to do is solve this simple set of equations. Mechanical equilibrium, it's a dynamic process, but the local accelerations are small enough that you can think of it as locally quasi-static. So the shear and normal stresses cannot vary through the layer. There's a conservation of energy, which says the rate of shear heating divided by specific heat, density times the specific heat per unit mass. That drives a temperature rise, but heat conductivity, where with a thermal diffusivity alpha, conducts heat away. So this is an energy equation. And then we must, of course, conserve the fluid mass, but the pressure changes as the fluid gets hot. So getting hot drives up the pressure, but the pressure drives Darcy-like fluid diffusion, and this term comes in. So that's the set of equations, and then we just take the point of view that the strength is modeled either as a constant friction coefficient or, somewhat more accurately, one that fits what is called a rate and state dependent friction law. So these are examples of calculations that we did. This was done with John Rudnicki and other co-workers over the years. But the first, Art Lockenbrook, a geophysicist associated with the U.S. Geologic Survey, had done a calculation like this in 1980, and we were just building on his solution. So he worked out the solution to that set of equations I showed you for a problem where these two blocks of rock above and below the fault zone are slid at a relative velocity v. The fault zone shears homogeneously, and he worked out what was the temperature rise and what was the fluid pressure rise. And of course, as the fluid pressure went up, the shear strength went down, and that was the thermal weakening process. But the question Rudnicki and I began to look at later with other coworkers is that solution stable? Should you really assume homogeneous deformation over a layer like that or not? And indeed, we found that the solution is unstable unless the thickness is extremely small. And I'll give you some numbers for what extremely small means soon. But in a series of papers, we worked out you would localize, and we could estimate the thickness of the localized zone. So the Lockenbrook solution is stable only if you have a thickness of the zone that is less than this critical thickness, which is what's said down here at the lower bottom right of the figure that you all over there have. But I'm sorry, I'm not pointing to that too. Okay, so now here's where do we get data to put in these models where, well, there have been lots of studies of materials taken from fault zones, so I won't go through details here, but suffice it to say we do have data for fault zone material and surrounding damaged material on things like permeability and other sorts of thermomechanical properties needed to do such calculations. Well, what do we get when we try to estimate the maximum thickness of a layer if it's going to shear and not have localizations within it? And this assumes reasonable results, we think, for friction, for various material parameters and the like. And a meter a second is a typical slip rate during an earthquake. So corresponding to, say, 7 kilometers depth, you could only have that Lockenbrook solution be invalid if the thickness was less than a few microns. So it suggests extreme localization of shear, which is indeed what is observed in the field. And if we, there's quite a bit of uncertainty in parameters, so blue gives us one limit to parameter ranges, red gives us another, but we're talking about 3 to 30 microns as a kind of thickness. So at 1 kilometer, well, this is at 7 kilometers depth. These are the corresponding numbers at 2 kilometers, at 1 kilometer depth. So this modeling of the process predicts very high localization, and this is a further illustration of that in a work with John Platt and John Rudnicki and me. And it just depicts the strain localization. So here's the strain rate plotted against thickness across that layer. This is a calculation. And you can see how this strain rate becomes very high in the middle and negligible as you move away from the middle of the zone. And this is well fit by Gaussian curve. It's not an exact fit, but the Gaussian gives us a way of talking about a width that's twice the root mean square in the Gaussian. And the width turns out to be of the order of 40 microns when we do the calculation for the particular material parameters looked at. And so it's small. So even if you start out not localized, if you try to shear fast like you do during an earthquake and you're fluid infiltrated, you will localize, and you'll localize down to something in the range of many microns, but certainly sub-centimeter range. Here's another study of that where we look. So what is plotted here? Here's the shear strength supported by the fault versus the amount of slip, which is written as the sliding velocity times time divided by the thickness of the layer. So it's kind of a measure of average shear strain in the layer. And what we see is the strength of the layer. It's normalized, so it begins its length at a strength of 1. The shear stress is equal to a friction coefficient times the normal stress minus the initial pore pressure. But of course, as the heating goes on, the pore pressure goes up and the strength goes down. And what you see here is the calculation that's represented by the blue curve. So the Lockenbrook solution that I described, assuming homogeneous deformation, gives the weakening that you see in the red line. And the blue line gives the result of our solving that set of differential equations I showed you. So there's even more weakening than the Lockenbrook solution predicts, and this ultimately begins to look like the solution I showed you for slip on a mathematical plane. So that's the mathematical form of it, but it indicates that you really have very significant reductions of friction from friction coefficients of the order of unity down to, down to much lesser friction as sliding goes on. Now, what else can happen at large increase in T in temperature? So just having ground fluid there and it getting hot is a weakening mechanism, but even more things can happen as the rock gets hot due to the high temperatures, and that is in particular that thermal decomposition reactions can set in. So carbonates release CO2, clays, serpentines release water, and of course the ultimate mechanism is melting. We do see occasionally evidence of melt and resolidification in fault zones, so it happens. But along the way, these decomposition reactions happen too, and there's lots of recent evidence, especially in studies done by geologists in Italy, in the Italian Alps, on finding evidence of carbonate decomposition there. So here is an evidence of decomposition, and this is in clay minerals after that Chi earthquake in Taiwan in 1999. Another is from laboratory friction test on calcite at high velocities. But you see the idea of a very narrow zone of slip developing within a wider specimen. Now, so these are examples of decompositions: dolomite, clays, and hydrosilicates, gypsum. Gypsum is a safe material to work with. You don't want to get too close to things that you have to do your experiments at temperatures in the ranges you see here, but gypsum does all of its action in temperatures that we can tolerate in the lab. So there are very informative experiments done in this case at ENS in France, in Paris, by Brantu and others. This is an example of the kind of testing machine that's used for the experiments. a rotary apparatus. And here's an example of what happens when you apply force. You take such an apparatus. Yeah, it's on. Okay, you take such an apparatus and you force one part to shear relative to another, and you measure the friction. So this shows a variety of different runs on that, but here the data is reported as friction coefficient versus slip rate, and the slip rates get up to more than a meter a second, so they are in the range of actual earthquake slips. And you see the friction coefficient measured diminishes substantially from typical static friction values in the range of 0.6 or so down to extremely low values in the range of 0.1, with increase of the sliding rate that the specimen is forced to sustain. And then we can also look at excuse me, we can also look at the shear strength at the as a function of normal stress, and this is in the range of slip rates of the order of a meter a second. So at the onset of slip, we have normal static friction in rocks with a friction coefficient around 0.6, give or take a couple hundredths. But then during slip at a meter a second, what we find is the friction strength is this effective friction of about 0.06 plus a very small factor, 0.01 times the normal stress. So again, it is severe weakening due to the thermal weakening process, and in this case, the weakening process is not just the heating of native pore fluids, but it is rather the generation of new pore fluids by thermal decomposition reactions in the parent minerals in the fault zone. So that gives great weakening, as you see. So naturally, we, being modelers, like to make calculations of what would be implied by the things seen in such experiments. So we set up the equations, as you see here, a heat or energy conservation equation, the top line here, and then the next line is a fluid mass conservation. We recognize, of course, that that comes down to an equation for pore pressure once we relate fluid density to pore pressure and temperature. So those are the equations that we have to solve, and we assume an Arrhenius kinetic law in these, where the extent of reaction begins at 0 and goes up to 1 when everything that can react did react. And this was done for a variety of lithologies of the rock, different temperatures of their dehydration reactions and so forth. So we could begin with a simpler calculation, though, which just does a linear perturbation estimate of the thickness of the localized zone. And we get something here which depends on these thermochemical parameters of the material, E and P, and they're kind of shown up here. They're combinations of these other parameters above, but they are functions of temperature and pressure, and are shown here for the decarbonation reaction and for dehydration reactions. So in any event, that's how the calculations are done. I'll not take you through all the gory details of that, but when we then plot the friction strength divided by normal stress and an apparent friction coefficient, this ratio starts out at 1 at the beginning of sliding, but as sliding goes on, first you localize, and that involves the help of pressurization of the existing fluid, but then the reaction sets in, and you're generating more fluid that comes out at high pressure from the decomposition reactions within the fault zone. And that finally takes you down to extremely small frictions, 14% of the initial friction strength after just 2.5 centimeters of slip, which is small compared to the slip in earthquakes that you worry about. So it supports the idea that faults, while statically strong, they're brittle in the sense that they lose strength quickly after slip is initiated and localization and then heating further weakens slip. These are just some movies or snapshots, not movies actually, of simulations which depict the localization, but this is a scale which in millimeters, so this whole section is 1 millimeter thick. The fault zone is horizontal, and you can see plotted here the different thermal parameters, the reaction rate on the right, and on the left is the strain rate. So you see that as you would expect, of course, the strain rate is initially diffuse but becomes highly localized due to all this weakening. Everything is happening in an extremely thin zone. Again, that's 1 millimeter scale. And the reaction rate, basically once the reaction starts, things weaken fast, but then ultimately you deplete the reactants, and then the effect of all of that is somewhat attenuated. But that's the way we've been able to model things, and there are some interesting things like once you deplete reactant, that the fault shows that it has some cleverness. The laboratory specimen, I shouldn't call it the fault, I suppose, but the laboratory specimen, instead of keeping its solvent shear in one place, it decides to move the shearing to other places which have not yet been depleted of their reactants, and so the net shear zone spreads in that way. Yes, so, and we think this kind of process may explain some observed lamination seen in fault zones. Here's an example from Tom Mitchell at University College London of a carbonate that was subjected to rapid sliding and underwent these decarbonation reactions, the kinds we're trying to calculate. He thinks the crack is an artifact of sample removal, but you can see the very localized zone, and you can note the size scale here. That is 100 microns across the thickness of the zone, and I forget the overall thickness of his sample, but it was certainly large compared to 100 microns. So again, you see the severe localization. Okay, so conclusions. We've documented weakening and shear localization by thermal pressurization of pore fluids, and they may involve either native ground fluids or the volatiles released from decomposition reactions. We have the flash heating process, which also weakens friction, the first process that I showed you. And melting, which I've not discussed, of course, is the ultimate limiter if these things have not weakened the frictional heating enough that you don't quite reach the melting temperature. It makes it clear that the static strength of faults is an unreliable predictor of pre-earthquake stresses on major well-slip faults. And we now think, and this is another chapter that I don't have time to explain, but we now think that faults might be living near or slightly close to a level that we call tau pulse, and it's a stress at which a small event, once nucleated, will propagate indefinitely without the aid of any weakening process of the type that had been presented. And then roughness could keep less mature faults from the full benefit, or full threat, perhaps I should have written, of dynamic weakening, to slide with less mature, less localized faults. The sidewalls have to be deformed, and of course this gives additional resistance. And the fact that a segment of fault is creeping doesn't preclude it from having large co-seismic slip. We have seismic examples of that. So I think that's the end of the story. Let's see what's next. Yeah. I could say that the future history of fault mechanics, which is something that I think I'm too old to contribute to, but former students and postdocs have been actually doing some of this program. It is actually to do elastodynamic solutions for models which have fault zones and which enforce these equations representing the thermal and chemical processes of heating and decomposition that go on during earthquakes. So that's the future, and some papers on that future are in the recent literature. Thank you very much.
Dear ladies and gentlemen, I believe we have no time and it's not a good opportunity for questions, but I will ask you for something else. Having in mind the contribution of James Rice, please have a standing applause for him.